So let's take a step back and look at the whole picture in the AI space. Let's have a like 100 miles overview. Here you see the relationship of complexity on the x-axis and performance in AI training, or you can like as proxy metric could be quality, accuracy, or anything, right? And most of those relationships look similar to this one, where we have kind of something that looks like diminishing returns. Usually it's like a power law relationship, where if we double the complexity we spend with those AI models in space and time, so in other words, space complexity would be the model size, time complexity would be the number of compute operations we need to train a certain AI model. If you increase those properties, so we have larger models, we train on more data, we perform longer iterations on our AI training algorithm and so on. So we invest more in terms of complexity, then we get better quality in general, right? And this curve, this might be true for, so this might be, say, the progress of humanity curve, right? So if we invest more and more, we get more and more performance out of it, and but the returns somehow diminish, right? And from time to time we see like small jumps in terms of performance without reducing complexity. So sometimes we might see something like this, where performance actually stays the same, but complexity reduces, right? So as we optimize something, this curve might move to the left a bit, right? Because we have now, for instance, with the 1-bit LLMs, we have made something less complex, right? We found a better algorithm to do something, so we have reduced complexity, but performance stayed the same. So that's why, like, all these like little improvements, they don't really improve performance. So those improvements don't actually improve performance in terms of moves humanity up this curve, but they move this curve to the left. So we need to spend less complexity for these kind of optimizations, right? And this is like one example of the 1-bit LLM that we have discussed in recent videos on the Finxter channel. And yeah, this is like this is how I see the world in AI. So we have two types of papers, two types of research. One type of research is just to move the performance up, to move this curve up, right? This is like on the edge. This is what OpenAI did with ChatGPT 4, ChatGPT 3.5, and so on. Yeah, so they just move this up. So they are on the march of nines, right? So they improve the accuracy from 99.99% or something to 99.999%, right? Something like this. So in self-driving, maybe they reduce accident rates, or maybe increase the number of miles driven without accident from like 99.99% to 99.999%. So we just have another 9 there. We reduce the error rate or the accident rate of our AI models by an order of magnitude, which means we just add 1 9 in terms of accuracy. So that's why it's called the race of nines, right? And so research is just like moving this curve up. So actually drawing a new data point here, drawing a new data point here in this space. So the new curve kind of looks different, right? And maybe also adding complexity, right? And we can see a number of papers. Is it this one? No, I have actually prepared a chart also that shows how complexity moves up and how performance moves up. And this is human progress, right? We push the boundaries in terms of pushing up complexity, pushing up the performance, and then moving this whole curve to the left by introducing performance optimizations such as 1-bit LLMs. But then also in this curve, we need to be aware that we can always, so maybe let's first have a look at a few examples, and then I will give you this takeaway. So here we see like an ImageNet fine-tuned error rate on the y-axis, and we see the compute on tensor processing units here the tensor processing unit on the x-axis, and we can see that how by spending more compute, actually let's make this a bit thicker. So by investing more compute here, we actually reduce the error rate, but it doesn't reduce like linearly or so. It increases, like we have some kind of diminishing return, right? So which means the curve kind of flattens out. Even though we need to be aware that that this is actually the x-axis here is a log axis, right? So this is the logarithm. The axis is logarithmic, which means that we have now increased compute by a factor of 10, by a factor of 100, by a factor of 1000, by a factor of 10,000. So in order to reduce the 10-shot error rate from 80% to say 10% or so, so going from here to here, we go from like 80 to 10%, but we have 10,000x. So this is 10,000x in compute. Okay, so this is already one big takeaway. We like many improvements just come with scale, and they can only come with scale. We need to throw more compute at these problems. We can make it more efficient, so we can maybe try to get the most out of the compute, but this won't change the fact that we will, even if we found the most efficient way to solve a problem, we will throw more compute at it. And it's actually a well-known theory in AI. It is called the AI scaling laws, which means that by throwing more compute, so we have found machine learning model theoretical ways of representing knowledge, like for instance deep neural networks, transformers, and so on. We have found knowledge representations in computing where we can throw more compute, more parameters. We can make them bigger. We can create artificial brains, make them bigger, throw more data into them, yeah, make them bigger. This here would be the x-axis. So we make those bigger. We throw more data at them, and thereby, by making them bigger, throwing more data at them, we reduce the error rate, and we improve the performance of these models. And we can see many, this is like very well documented in science. And OpenAI was among the first ones who actually pointed out, or maybe who were bold enough to scale computation to unseen levels before. So they have, on this x-axis, OpenAI had the boards to invest billions and billions to move from left to right, to throw more compute at the problem. And that's why I really appreciate what those guys did. They pushed humanity progress further. So basically, like in scientific language, you might say GPUs go brr. So we will print more GPUs. This is again representation of the scaling laws. We see compute increases, and by increasing compute, it is like wonderfully we still see a reduction of loss, and it doesn't stop. We can keep improving compute. It's like a power law relationship. You see in this block, right? You see this axis is a log axis here. You see 3, 4, 5, 6, 7. So the distance between two subsequent intervals actually reduces as you go up, which means that this is logarithmic axis. And here you can also see like a factor of 100 logarithmic axis. So if you have a line in log space, so both axes are logarithmic, and we have a line, this means it is a power law relationship. Now this power law relationship doesn't look like very significant, but it means that the curve, actually, if you wouldn't have a log-log relationship, the curve would somehow explode like a parabola, right? Like a parabol. So like something to the power of 2 would be a power law or something, right? So this could definitely happen. And you can see also that not only does the loss improve by, sorry about that, not only does the loss improve by scaling, by increasing the compute, the loss also reduces by increasing the data set size and the size of the machine learning models. And basically, compute is just a function of the data set size and the number of parameters needed in our models. And often we have, nowadays we have trillions of parameters, right? Trillions. So these are like thousands of billions of parameters. So we, and if we want to actually replicate human brains, like if artificial neural networks should become as large as human brain networks, we will keep increasing the scale significantly, right? So if you number of neurons brain, if you search for the number of neurons in the brain, you see that the human brain has like 86 billion neurons, right? But these are now the neurons, right? And now we have 100 trillion connections to each other. So, and these connections have different strength, and and as we learn, we kind of change the weight of the synapses, of the connections between two neurons, right? So we have one neuron and like say we have 3 neurons. Now this is a synapse, or a connection between 2 neurons, and this is actually where the learning happens. This is one weight, right? The strength of this neuron, this would be like a floating point number, say, or in the case of 1-bit LLMs, it would be like a ternary number, right? A 1, 0, or -1, or a binary number, even 1 or 0. So this weight would encode the learning somehow. Collectively, all weights together encode our learning from the data. And we can see now again, looking at the number, it's like the one human brain has 100 trillion connections. Okay, now let's have 100 trillion times the number of people on Earth. 100 trillion times 8 billion. It's like a number that is so insanely high. This is the number of weights needed potentially to just replicate the collective human computation power. And so we are far from this kind of scale, right? We have not even created neural networks, artificial neural networks in computing that have the size of a single human brain. Maybe collectively, all artificial neural networks we have created these days have like this kind of size, right? If you would like add together all the Llama 3 models and all the ChatGPT models, even though it doesn't make sense at all to add those numbers together, just to get an intuition of the scale. But I mean, we maybe use 2 trillion or so parameters, not 100 trillion parameters in our models. So compute will keep, and maybe this is the reason why it keeps improving, because we are just early stages in terms of scale, right? Nature has a lot for us left to learn, and as we scale computation up, the performance actually improves and the loss actually reduces over time. And this has been consistent over several orders of magnitude. So this is a very stable trend. And the only scientific assumption now you could take is that this trend will continue for now. You cannot justify a position where you assume that this trend won't continue for some time. Of course, it won't continue forever. If the loss is 0, it's 0, right? If you have perfect accuracy, it's perfect accuracy. We cannot improve upon this. So from first principle basis, it needs to end. But I think we are just at the beginning of these AI scaling laws. And we will see more and more papers as we approach the ends of the scaling laws. For instance, Moore's law also has persisted much longer than most people expected, and only recently flattened out. And I think it will be the same for AI scaling laws. It is very robust. It had persisted over several orders of magnitude, and it will probably persist a couple of orders of magnitude. So we should assume that we will just print out more GPUs or maybe even like ASICs, application specific integrated circuits, so ASICs for AI optimized, like maybe hardware that is optimized for 1-bit LLMs or something, right? So so the general idea here is it's just a beginning in terms of AI, in terms of what we are doing. In fact, to reach AGI, scale is all you need. Yeah. So here this is like the scaling law, 3 scaling law plots that are very powerful. And I found online somewhere in a blog that these 3 points, I think it makes sense to quickly go through these 3 points. This is the main argument, and you should be aware of this. The scaling laws say that with enough data and compute, we can reduce the total error to near 0. Now think of what this means for real-world AI applications in terms of, say, self-driving cars. We will reduce the total error to near 0, given enough data and compute. So we will throw more compute at this, more data at this, and the cars will drive perfectly. We will have an accident rate of near 0, and it will be completely automated. And the cost for mobility will drop significantly as a result. So self-driving, for instance, is one of the biggest AI applications in the world, unlocking tens of trillions of dollars of economic value for humanity. Because we don't need to drive anymore, right? The drivers are now freed up from their need to spend hours and hours and days and years driving, as imperfect as they are, right, with the high accident rate we have. So, and and millions of people dying in accidents will actually survive, and those brains can then be reintegrated into our collective economy, which means that it will produce huge, insanely huge economic value. And this is only one application, right? One application of the scaling law. I mean, there are many such applications. Think humanoid bots or so. Yeah, it's just all like human labor, where we will reduce the error rate to near 0, but just throwing more data and compute at this. And we create a new race of workers for us. So they will do the work for us that we don't want to do. And they can do all kinds of work for us. It's not just an economic function. What is the type of work that is valuable for us? And they will do it. And the error rate will approach 0, and they will be better than human being. And all that's needed, all that is between us now and this future we are expecting to happen, everything on this bridge here, going from our current state A to the future state B, is more compute, if you think about it, because the data is already there. And the data, you can generate the data by just doing stuff in the real world and observing observing the feedback of the real world. So you can, like, data is infinite all around us. Data is, you can think of data as growing exponentially, so it's growing faster than anything else. But data is not really growing exponentially. It's like just digitized in an exponentially growing way, right? Because the data is already there. I mean, just maybe if you have more and more camera data, it's just because we record more and more percentage-wise of what is already happening. But it is happening either way. And of course, we add new data, like data that is captured by social networks. But if you think about it, the data is created by humans, for instance, on the edge. And social networks only capture a fraction of the data that is actually created. So the data is already here, and we are growing into an infinite stream of data that is everywhere, all around us. And so as data is not the bottleneck is computation. It is just how much data can we actually process. And that's why, like, going from state A, from our current state, to the future state B, where AI is doing everything without loss, without error, and with a very low error rate, it's not a data bottleneck, it is compute. Compute is all we need, basically, to reach a scale. That is all we need to reach AGI. Good. The second point is the trend suggests that an LLM, large language model, with near 0 total error would have a performance of 90% on Big Bench, which would look pretty intelligent. Okay, so we don't need any new breakthroughs, just scale. Okay, and again, you can see like an expression of the scaling law here. We have the compute, we increase the compute, we increase the data, and we increase performance of our LLM. And this is everywhere, right? And the only solution, we don't need a new representation of data or something. We don't need new algorithms or anything else. We just need more data, which we have. So data is simple. Having more data, acquiring more data is kind of a simple way. I mean, it's simple but not easy. Yeah? Sometimes it's hard to get to the data in our world, but the data is there, right? I mean, the problem is very solvable to get the data. The challenge is compute. Compute is always a challenge in these kind of environments. So compute is a scarce resource and will remain to be. And I think this is a very practical takeaway from this more theoretical first principles talk. So what I also wanted to show you is like this Reddit post, right? Here was somebody like on Reddit 3 years ago, so which is like in the year 2021, when nobody really had like GPT, say GPT-3 or GPT-4. I mean, nobody talked about this because it didn't yet exist. There was one post, why do people think scale is all you need to reach AGI? Then there was one comment, well, we'll see in a few years when both pathways and GPT-4 are released. Think about this. At this point, this would have been an insider, and the comment actually was removed later on, right? So this is an insider who already knew about GPT. Nobody, like in 2021, only a few people actually knew about like GPT, what it is, and the version numbering and stuff. No, today, of course, everybody knows GPT-4, but I think it was like even before GPT-4 was known. It was like just a future version of this GPT model that was researched internally by OpenAI, and they saw that with each version they have like an order of magnitude improvement. So so this was when the comment was issued, right? And then, no, this is really funny. And then we had this guy, Paul Topping. It's wishful thinking, blah, 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 mid-curving it to the death, plus the assumption ANNs are all that is needed for AGI. When ANNs were invented, they were given a name that would trick many people into thinking they are related to the biological neural networks of the human brain. Blah, 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 mid-curving it over and over again. And this is, I think, it's a good meme, right? The mid-curve expert on AI. Don't be this guy. Don't be this guy, this one, because he will be wrong, right? I mean, you can decide. Do you want to be this guy? Just believe in AGI, right? Believe in AI. Just assume it will come, right? I mean, because this guy will be right. Don't overthink it. Or do you want to be this guy? Dive deep into the research. Subscribe to the Finxter channel, actually. So check out all our videos. Like this video, do the research, read the papers, think deeply about this revolution, and come to the same conclusion as this guy. They are aligned, right? They have the same conclusion. AGI is coming soon. But this guy, this mid-curve guy, this is like the Paul Topping from the wishful thinking comment 3 years ago. He couldn't have known that only 2 years later he would look very stupid with this comment, right? Only 3 years later, he would be addressed in a YouTube video making fun of him, right? He couldn't have known this. Nobody knew, right? 3 years ago. I mean, this guy, obviously, he was like this guy here was this one. He knew, yeah? But very few people knew about the concrete models that will accomplish it. This guy was just believing it, just on a very general way. Maybe he just was feeling it or something, right? If he was just thinking like 20, 30 years in advance, he was not overthinking it. He was already believing in AGI, but only the mid-curve people, the ones like with an IQ of 100 or 110 or 115 or maybe 120, only those kind of people who they gave their analyze and opinion, and their opinion was totally irrelevant, because if you know very little of a certain topic, your opinion usually is very irrelevant. You should not you should not trust your opinion too much. It is better to be this guy, just honestly and truthfully to yourself, honestly and truthfully, like making it, speaking to yourself that that you don't know. If you don't know, you don't know, right? But and then you are just, if you just tell it to yourself you don't know, then at least you won't be subject to the Dunning-Kruger effect. Good. Let's have a look at a few more scaling laws, figures. For instance, here we see compute. So we increase compute by orders of magnitude. This is again log scale, and the ELO, which is like a chess rating, and we can see throwing more compute at it increases the chess rating. So we have this kind of relationship, but it kind of flattens out. And also you need to be aware that here we have a logarithmic plot. So this is log plot, and this is like linear plot, right? Which means that it becomes harder and harder and harder to improve. But we will still improve. But just to be like, just like adding 10%, say, in chess skills, just adding 10% of your in chess skill in ELO rating, maybe it costs you 10x in compute. So the question is the economic value of becoming a 10% better chess player, does it justify to throw 10 times more compute at it? And often it is. Often it is justified. If you have just one Einstein more, like one Einstein in humanity, we have lots and lots of scientific progress. We accelerate scientific progress, and life on Earth becomes more efficient as a result. Then computing power used in AI systems. Again, we see like from 1960s to 2020 and beyond, we see like how significantly the computing power they spend calculating at 1 petaflop per second. This is the log scale. If something here increases linearly, this means we have an exponential increase in compute power. But then what happens after Moore's law, that was already an exponential increase, we saw an even accelerated exponential increase due to GPUs, probably. Most likely, yeah, I think this should be GPUs. This is like the NVIDIA effect. Think of this as the NVIDIA effect. It would have taken much longer without NVIDIA to reach the same number of flops with GPU. And this only assuming that we wouldn't have seen a CPU, an end of Moore's law era. Also, if you ask like collective intelligence, I'm a big believer in collective intelligence. We can see that we collectively assume that AGI will be reached between 2029 and 2040. And this is just in the next, if you do the math, 5 to 16 years. So most of us will see it in our lifetimes. Most of us will see AGI coming due to the scaling laws. And so the reason for this will be the scaling laws. And AGI, make no mistake, will change everything. It will change life on Earth. There are some limitations, and I didn't want to make this video about the scaling laws and give you like trust and faith in the progress of AI without also giving you the other side. We are somewhere here, somewhere in this region. It is questionable where exactly we are. So I personally would say maybe we are somewhere here, right? But we could be here as well. I mean, nobody knows for sure. But we are still in this region where we have a power law improvement of the error rate. So this error is a log scale error. And so we have a log scale on the training data set size. So if you have a line in the log space, like a straight line here, this means that we have a power law improvement of the error rate. And there is currently we are in this world somehow. And even if we don't change the models, even if we keep like using the same models like ANNs also, and we didn't find anything new, we just need to throw more data at it. This is all we need. Data and scale is all we need. And in order to throw more data at it, we basically mostly only need GPUs, only need computing, raw compute power. And then in some future point in time, we will converge. And as we converge, we need to find new models. But at this point in time, we also have AGI, hopefully, on our side, helping us to push forward the boundaries of research and to improve the error even further. Sometimes then, in some like future, we will reach the minimum error, the minimum error that is possible in our universe. And this, of course, would be the most optimized, most efficient place to be in. So some principles of deep learning. Why is deep learning so important? So if you think about it, we have traditional machine learning models. This might be now the, linear regression, yeah, something like this. So we have linear regression models, and by throwing more data at those models, we don't actually increase the performance anymore. So we converge. All models, all machine learning models eventually converge. It is only so interesting to see that like going from this state to this state was actually possible with deep learning network, with deep neural networks. That this kind of model that we actually took from biology, right? We just copied it plainly from biology, this representation of knowledge, and it actually allowed us to scale the performance up by throwing more data at it. And at some future point in time, we will also converge. So throwing more data at this representation of knowledge, like this is, say, the GPT LLM kind of representation, is not sufficient, so that throwing more data at it will actually result in an improvement of performance. But we are not yet there. We are like for the next, say, orders of magnitude in time and complexity, we can still keep improving. So we should simply now throw more compute at the problem until we see the convergence. This is our current state we are in as humanity. And as we have not reached convergence, all that is left for us to do is just throw more compute at it and see where we land, see where we converge. And chances are, because we have already reached superhuman performance in many ways, chances are that we will reach AGI with this one just scaling up push towards more compute. Essentially buying more and more GPUs from NVIDIA. So the big picture trend, again, it can be seen here. This is even in the log space. We see the number of parameters of our models over time has increased. This should be exponentially, right? Because now we are here, we have the log space. This is actually super exponentially. If you had a line here, this would mean that we would increase exponentially, because we 10x, say, the number of parameters for every 1x in time. For every one step here, we do 10 step here up. So the line would mean we have exponential increase of the number of parameters over time. But as we see that, like this growth curve here, we have a super exponential increase of the number of parameters of our models. And I mean, mind you, this is like a curve starting with in the 1950s. So do you think this curve will now suddenly like go down or something? It would be very unusual. So most likely the curve will go something like this, go up, and then somehow converge. It will be this kind of S-curve, right? And being an S-curve means that we will see significantly more compute demand again. Once again, one more data point that showcases that this trend will be sustainable, or in all likelihood. Nobody knows, but I think this is the position you should take today as a scientist. The compute complexity of AI training. I generated this graph with ChatGPT myself. You can reject it, or you can just look at it. You see, again, we have a log, so log in data size versus log in compute requirements or unit for AI training. So if we increase the data size, we basically also increase our compute requirements. It is some kind of power law relationship. So we have maybe a quadratic increase of compute requirements or so. as we increase the data size. So we are already sure that we will increase the data size because of the AI power laws, right? So by increasing the data sizes means we also increase the compute requirements, but maybe it is even more than linearly, right? So doubling the data size could maybe 10x or quadrupling or something, the compute requirements, which would mean that we will basically need more NVIDIA AI compute. So, and you can see again here the curve. We in 8 years, from 2016 to 2024, we have seen 3 orders of magnitude, 1000x in the number of operations, teraflops operations, going from 19 teraflops to 20,000 teraflops with the Blackwell infrastructure. So NVIDIA provides us with the compute to do it. And now there are 2 forces you should be aware of. Mind you, nobody has the answer to which force is more powerful. One force is digitized data. The data volumes continue to grow, which obviously leads to more compute demand, right? If you have more data, so if you double the data and you use the same model, you need to double the compute, at least, maybe more. But if you double the data, you usually also increase the model size. But as you increase the model size, your compute actually goes up with the data and goes up with the model size. So your compute goes up faster than the data growth and the model size. So which means that in the future, we will see more like extremely high levels of compute demand. This you can be sure of. Like this is a sure bet to take, right? We will have significantly more compute demand. Now the problem, like the one question, the one concern also I have is the cost of compute continues to fall. And it usually falls like with declining cost curve, something like for every doubling of the cumulative production of compute, we see a constant percentage improvement in terms of cost. Or there's another, like this would then relate to a power law cost reduction curve, but some people also argue that the number of flops per second, the number of flops, so operations per second, the compute per dollar, actually doubles every 2 or 4 years. If this would remain true in the future, like no matter, it could be 2 years, it could be 3 years, it could be 4 years, but if this trend would persist, this would mean like an exponential increase in compute per dollar spent. And if this is the case, then actually the revenue might go down. The revenue for compute, like for companies of providing us with compute, the total revenue, because you multiply something, you have this one force, the scaling laws that grow the total demand for compute. So more and more businesses purchase compute tokens. But if the cost for this compute goes down, the total revenue generated by selling compute might go down as well if this trend is too strong, right? So here the takeaway is revenue for NVIDIA and other like AI chip manufacturers will only increase if the compute demand grows faster than the cost of compute drops. But now now this is kind of the relationship. Now this is objective, the objective relationship, yeah? So you should be aware of this. Now I give you my opinion. My opinion is that the digitized data, this one, is unlimited. You could think of it as exponentially growing, but in reality it's unlimited. We have so much data in the universe, we can never capture all this data in the universe. And but the more data we capture, the more intelligent the entity capturing and processing the data becomes. You can think like a godlike entity, or maybe think of it like in Doug Adams' Hitchhiker's Guide Through the Universe, where he created a computer that was actually the Earth. So the Earth itself was the computer. So, and it was capturing all this data as part of its own internal computation and simulation to find the answer of the universe, which was then 42. No, actually to find the question for the answer, and we already knew that the answer is 42. Okay, so you could think of it like this kind of satire, but that's why, because I think this one trend towards more and more capturing more and more data will dominate all the other trends. It will still be true that we will use larger models, right? And it will still be true that the compute reduces, cost per compute reduces for some time with research and so on. Yeah, but we have seen with Moore's law, eventually it comes like the cost per compute cannot be significantly reduced per compute operation. We are long away from this point in time, but at this point in time, at this future point in time, I think the data volumes will still keep growing. And this is only my opinion, but I think it's rooted in first principle, and yeah, take of it what you want. And me personally, I think the revenue for NVIDIA will grow significantly in the future due to the significant increase of compute demand. But this slide just gives you the relationship between these two forces. First, we have the growing demand for compute that we can be sure of, and then we have the exponentially dropping cost of compute per compute unit. And it is just like which force is larger. It is a competition between these two opposing forces. And if you think about it from first principles, what is compute anyway? Compute is just data processing capability. So we take some data, we process the data, we get something out of the data. And what is a human? I mean, a very rough, crude level, human is a data processor, right? You get data in, like the learning, like the conversations you have with your mother, with your brother, with your friends, the books you read, the YouTube videos you watch. By the way, subscribe to the Finxter channel. The movies you watch, the observations you make, moving your body through the physical space. Like all a human basically is, at least thinking of a human economically, is just being a data processor. So what compute really is intelligent labor. And so compute is you do some work, right? In order to come to the conclusion, in order to process the data, you need to invest some labor. It takes labor to do it, right? And even if you manipulate something, you kind of manipulate a physical state. So computing kind of manipulates a physical state, if you think about it. It's like manipulating energy in a way. So you have some data processing, and data now in a very wide sense of the word. So compute is simply labor. Compute is like you thinking, or somebody, a researcher, thinking and writing a research report. And so one unit of compute is like the same as one as a unit of human labor. It could be like more or less disruptive, but it's the same DNA in a way, right? Because you manipulate the state of the world, you reduce entropy in a way. And so what it means basically is this fundamental relationship coming from something we already know, like human labor, to something we are afraid of, which is like AI labor. And basically going from wages we pay to human laborers to cost per tokens going to AI laborers, right? So we pay for the tokens, we pay for the AI work, we pay for AI labor. So basically the wages, they remain constant, right? We have constant, say it's like $10 per hour. Maybe tomorrow it's $11 per hour. But it always like it is in this range. And then you have some inflation adjustment, but like the wages don't change significantly. They stay the same. Whereas the cost per tokens you need to pay for AI labor falls exponentially. Yeah, so it falls exponentially. So over time, it will become more and more attractive from first principles to hire AI labor. So the relationship, the percentage, the market share of AI labor to human labor, if you think of it like if you have this market share, and currently maybe most of the work is done by humans, but the percentage done by humans will go down, and the percentage of labor done by AIs will go up in the same way. And we will see this crossover point. And Amazon, for instance, we have already seen this crossover point where there are more robots than human workers. So from a first principles thinking basis, we will see revenue going from the labor share of the GDP to AI, because the labor share of GDP, which is like roughly 50% of the gross domestic product of an economy, goes to human beings for their labor. But this share, this 50% of the GDP, will now go to AI, and specifically to AI infrastructure and services. So a portion of it might go to AI chip producers like NVIDIA. Another portion of it might go to AI services like ChatGPT subscription, or Microsoft, or AWS, or something. Yeah? And this will just happen, and we will see that like almost like in the end state will be 99% of the labor is done by AI, which means that from our 109 billion GDP, 50 billion goes to human labor. This 109,000 billion, so 109 trillion. 50 trillion of this goes to human labor currently. So 90% of this, like 45 trillion or more, will go to AI in the end. And the end might not be far away, as we've seen like in these estimations, right? The end might be like just 10, 15 years away. So from this first principles thinking, if we just assume that one company like NVIDIA, that is like the working horse of AI, maybe captures 2% of that. This would already make it like a $1 trillion revenue company, and a 500 billion actually, I should do the math correctly, 500 billion net profit company with a 50% margin they currently have. They even have a higher margin, but just assume 50% of the 1 trillion revenue goes to the bottom line. Then we will already see like a 500 billion net profit company with a say 30 PE or so. We will see a valuation of 15 trillion. Currently it's like 3 trillion or so it will be a 5x in this end state, in this 10 to 15 years or so, until we see AGI and integrate AGI into this world. This is this is a very crude way of analyzing it. I mean, this could be really anything, right? It could also be 0.2% or 20%. How much percentage capturing NVIDIA does. But as we have seen in this talk, as I have tried to outline in this talk, is that the limiting factor is not so much kind of services or something, or new research that we need, or new researchers, new ideas, or anything else. The limiting factor is just compute. So assuming 2% might even be a little low, 2% of that going to a company like NVIDIA, because NVIDIA provides the main value for this future, that is needed for this future to happen. Okay, so I hope you got the main ideas out of it. I wanted to give you like this design space of optimization, the relationship between complexity and performance, the takeaway that scale is all you need. AGI is coming with or without 1-bit LLMs. 1-bit LLMs are like, they are interesting, an interesting tweak, interesting optimization, but they don't change too much in terms of performance, right? They don't improve performance. They don't help us go up, like producing a leap in performance of our models, which is basically what we need to reach AGI. They just help us moving this curve a bit to the left, which is nice and pretty, but not too revolutionary. So we should not overhype maybe this one research paper. And I gave you the first principles. I give you all the statistics and data to undermine my thesis that compute will explode, and that computing, the demand for compute will most likely outstrip the cost decline of compute. So we will see higher and higher revenues for companies like Nvidia. Thanks for watching, and see you in the next video. Bye.